Welcome to Lab 6 of ECE2300. This laboratory will cover diodes, and although this laboratory is long, you get to look at quite a few circuits. The circuits are fairly straightforward, however. We will review the types of diodes that you're going to use in the laboratory. These include the small signal diode, rectifier diodes, and we'll look at both the half-wave rectifier and the full-wave rectifier configuration, Zener diodes, and light-emitting diodes, or LEDs. You may think of diodes as a one-way street for current. Current flows from the anode to the cathode. A reverse potential will block current flow from the cathode to the anode. On the schematic symbol, the straight line at the end of the arrow indicates the cathode end. The diode package will always have a stripe on the cathode end of the device. The voltage drop across the diode can vary from 0.2 to 1.2 volts depending on the type of diode. The most common voltage drop associated with a diode is about 0.55 to 0.65 volts. You'll need to take the voltage drop into consideration whenever you're using a diode in a circuit. Zener diodes are used to set specific voltages and are manufactured with a specified voltage associated with the breakdown. You can buy Zener diodes anywhere from 1.8 volts to 60 volts. Because the Zener voltage is a reverse breakdown voltage, current flows through the Zener from the cathode to the anode. Note that this is the only exception to the current flow for diodes in general. This is often very confusing for someone who's not used to using Zener diodes. Since Zeners are used to set voltage, the direction of current flow is usually not an issue. We will use the lower symbol to indicate a Zener diode in our schematics. LED stands for light emitting diode. Current flows from the anode to the cathode in an LED. The current passes a gap doped with a specific metal that results in the color of the LED. The longer leg on the LED is the anode. If you can see inside the LED, the cathode is usually a larger contact. Some LEDs have a flat side on the base. This identifies the cathode. The safest thing to do is use the longer leg to identify the anode on your LED. You need quite a few lab supplies this week. You need these values of resistors in these quantities. These diodes, and by the way, the Zener diode looks very much like the small signal diode. To tell them apart, look for the 4148 on the small signal diode and a 231B on the Zener diode. The transformer is not part of your laboratory kit. You will be given the transformer by the lab monitors or lab instructor. Please be sure to return the transformer to the laboratory staff once you are finished with the lab. You will need the usual equipment: the breadboard, the oscilloscope, the function generator, and the power supply. You'll need your BNC to mini grabbers, BNC cable, and your T adapter, which should be present on the channel 1 output of your function generator. You're going to need a few more banana to mini grabbers for the power supplies and the digital multimeter. Don't be afraid to stop the video while you get out these supplies. I know there are a lot of them. These are what you're looking for in the cabinet this week. The only thing we're really adding here are the banana to mini grabbers that you're going to use with the digital multimeter and the power supplies. The first test setup is identical to what we've been using in the previous labs. The T adapter on the function generator is connected to the BNC cable and channel 1 of the oscilloscope. And then you use the BNC to mini clip cable for your input signal from the function generator, as well as to measure the output on channel 2 of your oscilloscope. Circuits we're going to look at include the half-wave rectifier, and we're going to look at that with two different kinds of diodes. We'll also look at the inverting half-wave rectifier. By far the most complex circuit we'll build today is the full-wave rectifier. Then I'll show you how to set up the current in a light-emitting diode. For the Zener diode, we will be characterizing the voltage knee at different currents, and then we'll use them in a clipping circuit to show you how you can limit the input range for your signals when you're trying to protect the input of a circuit or an instrument. For the first circuit, you will need to set up your function generator as a sine wave, 5 volts peak to peak with 0 offset. But you need to change the frequency from the default value of 1 kHz down to 100 Hz. The first measurements that you need to take are the peak voltages for the half-wave rectifiers. What we're trying to find is the voltage drop across these different diodes. Remember that the diodes don't start conducting until you have exceeded the forward voltage for the device. To measure this, look at the difference in the peak voltages of the input and output waveforms. For the rectifier diode, we will see what happens when the frequency becomes too high for the diode to handle. This is the first half-wave rectifier circuit. The 1N4001 is a rectifying diode, which can handle more power than a small signal diode, but not as high of a frequency. It is adequate for 50 to 60 Hz AC signals encountered in line power throughout the world. Connect the 100 Hz input to the anode of the rectifier diode. Use a 1K shunt resistor and observe the output on channel 2 of the oscilloscope. Measure the peak voltages and calculate the difference for the first table. Be sure to only measure the positive half of the voltage swing on the input signal for your comparison. We are not interested in the peak-to-peak voltage, but only the peak voltage, which is between 0 and plus 2.5 volts. Before you move to the second circuit, go ahead and increase your function generator from 100 Hz to 100 kHz and observe what happens to the waveform on the output of the half-wave rectifier. Now swap in the small signal diode and observe the half-wave rectifier at the 100 kHz. Then go ahead and measure the peak voltage difference and calculate the forward voltage for the small signal diode. For this circuit, reverse the direction of the small signal diode and observe the waveform on the oscilloscope. For this case, you want to measure the difference between the minimum voltages of the input and output waveform. Record your results in the table for circuits 1A, 1B, and 2. For the full wave rectifier circuit, you will need the function generator set up for a 10 kHz sine wave. The amplitude of 5 volts peak to peak with 0 offset is fine. Build the full wave rectifier circuit using the transformer that you were given by the lab monitors. Be sure to use the 1N4148 diodes to construct the full wave rectifier bridge. A 10 kiloohm resistor is placed between the bridge output and ground as a load resistor to draw current from the rectifier. Connect the function generator to the input of the transformer. Connect channel 2 of the oscilloscope across the load resistor on the output. If you have built the circuit correctly, you should see that both the positive and negative half waves of the input signal are rectified such that both half cycles are now positive on the output signal. Measure the peak voltages and calculate the difference between the input and output just as you did for the half-wave rectifiers. The full-wave rectifier is the first stage of a DC power supply. Before the DC voltage is regulated, the ripple in the rectifier must be reduced by placing a capacitor in parallel with the load resistor. In power supply designs, this capacitor is very large and is chosen to limit the ripple for the maximum amount of current that the supply can source. In other words, the capacitor is matched to the lowest value of load resistance that the supply can handle. For our meager 10 kiloohm load, we will place a 0.1 microfarad capacitor in parallel with the resistor. Once you have inserted the resistor in parallel, measure the peak-to-peak voltage of the ripple that remains on the rectifier output. To do this, it may be easiest to change the coupling on channel 2 of the oscilloscope from DC to AC. This blocks DC voltage at the oscilloscope input and forces the signal to be symmetric about 0 volts. I will review how to do this in the video portion of the lab. But don't hesitate to ask the lab monitors for assistance if you have trouble setting the coupling to AC. Be sure to change the coupling back to DC when you're finished with this measurement. For the next few circuits, you will be using the 12-volt power supply. Use the plus output of the dual section for 12 volts. The ground from the power supply should come from the black connection of the dual section. You will use the digital multimeter to make current and voltage measurements. Just to refresh your memory, the dual section are these three connectors on the right-hand side. Be sure to use the common in the middle, the black connector, for ground. And remember once again that the negative supply is on the right. The positive supply is to the left of the common. So don't end up using the minus 12 volts by mistake. Before you build the LED circuit, calculate the value of the resistor that you would need for 10 milliamps to flow through the LED. Use Ohm's law to do the calculation. Assume that the voltage drop across the LED is 2.1 volts. Once you have come up with a resistor value, build the circuit with the meter in series between the resistor and the LED and measure the LED current. Record the resistor value and your measured current in the results table for the laboratory. It's important to know that the Zener voltage varies over a range with the amount of current that passes through the Zener. For this part of the lab, you will measure the Zener voltage, which nominally should be 5.1 volts, with three different values of resistors. Begin with the 1K ohm resistor in this configuration. Connect 12 volts to the resistor and use the digital multimeter to measure the voltage between the cathode of the Zener and ground. For each of the resistor values, you will also need to measure the current through the Zener in series. I suggest putting the meter between the resistor and the Zener. Measure the current through the Zener and the voltage across the Zener for resistor values of 150 ohms, 1K ohm, and 4.99 K ohms. Record the results in the results table for the lab. Now go back to your original setup of the function generator and the oscilloscope. Change the function generator to 20 volts peak to peak and set a 1 kilohertz frequency. Construct the clipping circuit by connecting the function generator to one side of the 1K ohm resistor. The other side should be connected to two shunt Zener diodes configured with their cathodes connected in between them as shown in the schematic. Observe the output on the other end of the 1K ohm resistor. Measure the voltage limitation imposed by the Zener clipping circuit by measuring the maximum positive value and minimum negative value of the output signal. The results table is divided into sections, and I strongly suggest having the lab monitors or the instructor check your results once each section is filled out. If you wait until the end of the lab and your results are completely filled out, you may have to go back and reconstruct some of these circuits to retake measurements. That completes the PowerPoint presentation. You should now go to the video portion of the lab.